Off we go. The derivative is a rate of change function. So we start off with some function. Often we use f of x, but it could be anything. I'm going to use h for my function. H is for height. H is a function of t. T is time. And let's do a quadratic. How about negative 4.9 t squared plus 10 t plus 2. And let's say h is the height in meters, and t, I should say h equals, t is the time in seconds. And I just threw a ball straight up into the air, and that's what this equation could model here. We know we have a thing called the derivative, and we usually put a prime on something to take its derivative. And so that would mean for us so far to take the limit, if we use the h, I'm going to use the delta x version, as delta x goes to 0 of h, I guess it would be a delta t. Keep your variables straight, Gary. Delta t, a little change in time there, of h of t plus delta t minus h of t all over delta t. Right? And that is just like what we've been doing. Often we use f of x instead. And so we would say f prime of x is the limit as h. Now here I'm using h in a different way. Here h is height, here h is a little change in x. I think delta x is better, or delta t, but our book likes h. F of x plus h minus f of x over h. So these guys are really the same thing, just one is, here I'm playing with times and heights. Here I'm playing with a function called f and x and a change in x called h. So this is the derivative function. Now, often this difference quotient here, we often will do like a dy delta y over delta x. And that h is our delta x, so delta x is going to 0. So when I take the limit over here on the right as delta x goes to 0, that's a 0, believe it or not. You'll see notation where instead of a delta, they have a d. Instead of a delta, they have a lowercase d. And this right here is just another way to write f prime of x. And these changes in x, and a change in x here is something like 0.1 or 0.01 or 0.001, for example, they turn into what we call a differential. So this notation right here is called differential notation. For a derivative. And throughout the course, we're going to play more with that differential notation. It turns out to have a pretty important use in this part of calculus and beyond. So a differential is an infinitesimal change in x. It's so small you can't even measure it. It's as close to 0 as you could ever get, unimaginably close. All right, so here I could do a similar thing. So just notation-wise, instead of calling this h prime of t, I could say this is the derivative dh of height over time. So often when I speak that, this would be the derivative of height. And then we usually say with respect to time. All right, so that's the formal phrase that this fraction means. Is just another way to write the derivative. Sometimes we'll break it out and we'll write derivative with respect to time like that. And then in a square bracket, we'll put what is the function we're taking the derivative of. So in this case, I'm doing negative 4.9 t squared plus 10t plus 2. So there's a bunch of different notation we'll see. Sometimes it's the prime notation, sometimes it's the differential notation, and they both essentially mean the same thing. And the differential notation references the variable, just like the function notation references the variable. So just some notation there. Now, let's go back to my idea of height. If I find the change in height over time, right, this is my dh dt. This is my h prime of t. I've made this new function. That new function was based on a change in height, which is measured in meters, divided by a change in time, which is measured in seconds. So although the height is measured in meters, the derivative function here has a unit of meters per second, which is velocity. Talked about that on day one. So I'm, this ball is flying up into the air and it goes up, and as it's going up, it's slowing down, and then it starts to drop slowly and it picks up speed as it comes down. The velocity is changing over time, this function right here. And if velocity changes, if instead of looking at the rate of change in position, we look at the rate of change of velocity, so new problem, rate of change of velocity, that's acceleration. And what that means is we want to take the derivative of the velocity function. So I have a velocity function, v of t, let's call it, which is also h prime of t. And I want to take the derivative of that. So if I take the derivative of velocity, that gives me acceleration. We'll call that a of t, a for acceleration. And remember, velocity is the derivative of height. So what I really have is the second derivative, two little apostrophes there. Right, so this is second, acceleration is the second derivative. What does a second derivative mean? It means take the derivative once, get an answer, and then try to take the derivative of that. So second derivative of height. And based on this notation over here on the left, we took the derivative once with respect to t of something, and then we take the derivative again of that something. And the neater way to write that is the second derivative, d squared. It's not really a square, it's second derivative with respect to time twice. So that's another notation we'll see for second derivative. Sometimes it's a double prime, sometimes it's a d squared over dt squared of whatever function we're playing with. All right, so away from the theory, let's put it into practice.